Good morning, Ron. We continue our conversation from last time. Let's use this. Oh, just a minute.
We just close the door here.
I was drawing. So we are talking about function fitting, right? Do a quick rewind of a quick reminder of what we did last time, really quick one, and continue. So we were talking about function fitting, function fitting. Let's see. First, we had a bunch of points, right? X and Y, like x1, y1.
But I don't see your board screen.
I forgot. Yeah, thank you for telling me. I always forgot to do the sharing. So just a minute. Share screen. Okay, do you see it now?
Yes.
Great. So we are talking about, that's a reminder of what we were talking about last time. So this is the cloud of points, x1, y1, x2, y2, until endpoints.
Yeah, but remind me, we are now speaking about xi being numbers or being
yes, I will.
Whole set of pixels.
Yeah. I'm talking about what we talked last time.
Numbers. Okay,
So we were talking about the function. What?
Your xi's in this case are numbers.
Okay. Yeah, numbers, exactly, just numbers. We were talking about the very, very simple case of a function from a number to a number, from x to y. Each of them is a number. And this, we call that a cloud. We denoted it with the letter C. And it
why
was,
cloud? Because there are many of them. Why do you call it cloud? It's very strange.
Yeah, do you have you want to call them a nebula?
No, just because there are many and there
Yeah.
kind of,
if you have a better name, I don't want it to be connected to the cloud, the computer cloud or anything, just like many, many points. Okay? Okay, and they are fixed. They are given to us. We don't change them. And now we want to find a function that fits them, something like that. And that was the first thing. We had this cloud, and the second thing that we
not any function which is in your case
exactly
2-degree
polynomial. We say, I will say it like that: agree upon a family of function, which will be parametric family. So now we were talking last time. We were talking about this family of function that were determined by two parameters, a and b. A, it was a second order polynomial, right? That was the family of function we were talking about, and I will denote it like f of a and b, because for any a and b, I have a different function, right? And from this family, we are looking for the best candidate, right?
We are looking for the best a and b.
The best what?
A and b.
The best a and b, exactly. Each a and b determine a candidate, and we're looking for the best candidate, the best fit. What was the next time we needed to define? You remember?
To define what?
We need to define a loss function, a distance, right?
Yes. How bad is your function? Yes.
For any candidate determined by a and b, we defined a loss function, which is how bad are we doing, or how bad are we doing? So loss of a and b, and I will denote here that it's respect to C, which is constant, right? The cloud.
Is loss the common name?
Yeah, that's the name we use.
It's a very strange
name. That's part of the terminology of deep learning, yes.
Yes. Okay.
If you were to choose this name, what would you have picked?
Badness.
Badness.
How bad it is, yes. Okay.
Cost. Cost might be a good name.
No, it's not cost. It doesn't cost you. You're just way off the distance from the real one.
But you know, when you say distance, you imply that it's a metric, but it's not always a real metric.
Okay. Okay. Loss. Loss.
Yeah. Loss. And we define a specific loss in our example. We could have chosen other losses, but the loss we've agreed upon was the square distances, right?
Sum of this, yes.
The sum of the square distances, right? So yi minus f, and I will denote it. It's this f of a and b, right? It's not just f. F of a and b of xi, right?
And you want to find the best a and b.
Okay. Yes, our goal is to find the best a and b, exactly.
It's a standard minimization problem. Okay.
Pardon? Yeah, it's an optimization problem.
Optimization problem. Okay.
Minimization problem, exactly. So we constructed a new function, right, of loss. This is loss, which is a function of what? Of two. Note that the kind of a switch in roles, like A and B used to be parameters, which is like fixed number, right? But now there are arguments, right? Or parameters.
There are knowns.
Pardon?
There are knowns or variables. You don't know them.
But you know, I want to emphasize something. It's not just that they are known. When you have a function, x is something that varies from a range, right? And a parameter might be unknown, but it is fixed in this context of this conversation, right? But we switch the role between the parameter and the arguments. Now,
this is confusing what you're saying now. It's not you're looking for the best f. Looking for the best f means looking for the best a and b. So they are not fixed, they're variables, and you want to find the best. Okay.
Yeah, but a and b, which used to be parameters for f, are now the arguments for loss, right?
Obviously, yes.
Obviously.
You're looking for the best of it, yes. Okay.
I want to emphasize this point because we're going to derive in respect to a and b, like arguments. Yes. Okay, that's an important point, I think. And it's confusing. That's part of the reason people are confused about it, because of this switch of roles. Anyway, so here we have a surface, right? Because it's three-dimensional. Actually, because we are human and we are limited to visualizing things in 3 dimensions and not more, that's why I fixed one of the parameters of the second order polynomial and left only 2 degrees of freedom, because we had another one like C, we could not have drawn it, right?
Okay.
So so we look for like I don't know how to draw it. Like if it's a surface, then this is like something like this. We look for the smallest point here, right? Okay, that's what and also after we did all that, we were talking about gradient descent, right? After we defined all the above, we can do gradient descent. Can you repeat what gradient descent is?
Yeah, that's the most, first of all, that's the most standard optimization method. So you always go, you're on a mountain, and you go, in your case, you want to minimize, so you go in the direction of maximal slope or maximal negative slope.
Negative one, right, exactly. exactly what you said, and let's formalize it. What should I do in it? If I have A and B and I'm in a specific A and B, how will I improve it?
No, you need to know calculus now. There is no way around it. I mean, this is not.
I agree. You need to know
terribly trivial, a
calculus.
bit trivial, but not so trivial. That
Yes,
you
we
go in
talked
the direction of the gradient.
exactly. The
Minus.
notion of the gradient is important. Suppose you know basic calculus and you know the notion of gradient. What do you do?
You
How do
go
you
in the direction
update
of minus the gradient because you want to go down.
exactly minus the gradient? And we also added another parameter which we call the learning rates. Do you remember?
Yes, yes. So
Okay.
the gradient tells you the direction, but you don't know how far you want to go. So
Yes.
you decide I'm going today only 1,000.
Exactly. We don't want to make too big steps in. We might skip the optimum. We don't want to do too small step because it's going to take us a long time to converge. So we have a parameter that controls the size of the step, which is a fraction of the norm of the gradient. So what should I write here? It's of A, so it's partial derivatives, right? Of loss with respect to whom?
To A this time.
To A, exactly. And is this
But
a
you
function
put there
of?
a minus sign before the LR. The LR should probably be positive.
Yeah. Sorry, you're right.
You're going on the minus negative
My
direction.
mistake. I write it as it was gradient ascent, and we're doing gradient descent.
Yes.
By the way, it's really easy to just put a minus on the loss and then.
Yes. Well, probably you want it to be in positive. So.
Yeah. So this is a minus. Thank you for correcting me. And is this partial derivative a function of one parameter, so argument, or two arguments?
No, it's two. It depends also on B, of course.
Exactly. It's a function of.
It depends on where you are on the mountain.
Okay, so B also plays a role here, right? Okay, and the same goes to the other parameters. So for each parameters that defines our parametrics family, we need to do this, right? Here we have two, but in the future we'll have many. Okay?
Yeah.
So this is important. I will, we call this the update steps, okay? And just one more thing, if we remember, we were talking about contours like in topographic maps last time. You remember that? We were talking about places like Mitzpe Ramon. And when we talked about a gradient descent, we said that we are going like that, right? That's the algorithm. Okay, we reached this point, and until now, we talked only about really simple case, a function from a number to a number. But remember that originally we wanted to build a classifier of images of dog and cat, right? Let's go back to that. But everything we did here, look, I will, do you see we have here, we have four things that we did. Everything we're going to be relevant to the case of a classifier of dogs and cats. Okay, so dogs and cats. So we have an image as an input, right? Like of a dog or a cat, right? What is an image in a representation for a computer?
Set of pixels, yes, matrix, okay.
It's not a set, it's actually, yeah, it's a matrix. This is a dog, right? Okay, so for the computer, it's just a matrix of number. Actually, if it's a colorful picture, it's a tensor, right?
Okay.
Okay, but for now, let's think of it as a grayscale image. So it's a set of number. How many of those? Like in a typical picture you take with the phone, do you know how many pixels you have?
No, no. Tell me.
It's about 1 million or several
Million?
millions.
Okay.
So let's think we don't want to use a matrix, but we want to use, we're going to flatten it into a vector, okay?
Okay.
So for each pixel, we're going to have a number. So we're going to have a vector, let's call it x, okay? X, is it a good notation for a vector?
Very good, yes.
Okay, so x belongs to, let's say, Rn. So n will be 1 million or 2 millions, right? Really big number. I'm not very good at imagining functions from several million dimensions. Are you?
No, nobody is. Okay.
Nobody. Okay, that's the domain. What about the image? I mean, of the function of the classifier. We want to take an image and what to do with it?
The image, sorry.
We want to build a classifier, right? That's our goal.
Yeah. So you assign a number or a vector to every vector.
Yeah, so we have two options only, right? A cat or a dog.
Okay.
So
zero.
Pardon?
So it's a 0-1 function. Okay.
It depends on how you want to represent it. You can represent it by 0 and 1, but I will choose to represent it by two vectors. One of them will be 1, 0. This will be a dog, for example, okay? And the other one will be a cat. Why do I do that? I'm going to turn it into a probability, actually. I want it to have a confidence level. So I want my function to be able to say something like that. Point 2 and point 8, and that will mean, let's write, this is a dog, and this is a cat. I want the semantic to be as follows. If my classifier will say this, I will say my classifier is 80% sure it's a cat. You understand?
Yes.
Okay. So the function I'm building is not from a number to a number. It's a function from Rn, right? Into actually the simplex, right? It's not the whole R2, right? It's just the probabilities of R2, right?
So it's to 0 to the interval 0, 1, no?
I mean, my image will be all the two-dimensional vector which the coordinate adds to 1, which...
Yes, which is equivalent to the interval. Because if you know the 0.2, you already know what is the other one. It must be 0.8. So
I agree.
You're giving one number, the probability of
in two dimensions, it will look like that,
yes.
Right? It's a simplex, but it requires only one degree of freedom, and the other one is determined by it, right?
Yes.
Okay, fine. Okay, so we have this function we want to learn or to know. And what about the cloud? Let's remember, point 1 was the cloud. What will be the cloud now? Look at the cloud. The cloud was just X and Y. What will be the X and what will be the Y now?
So the X's are going to be matrices?
It's no longer matrices. We flattened the vectors, right?
Vectors, okay, so vectors.
Yeah, so let's talk about the cloud again.
The y's are also vectors.
Exactly, but let's put it as an example. Like the cloud will be like a flattened picture of a dog like that, right?
Mm-hmm.
Comma, a dog. Okay, this is a dog.
Mm-hmm.
This is one example. The one XY.
So in your examples, they are deterministic. They are sure either it's a dog or a cat.
Exactly. Yeah.
Okay.
In my examples, I'm sure it's a dog or a cat.
Okay.
Exactly. So this is one example. Let's give another example of a cat. So it's another image, flattened image like that. And I'm sure it's a cat. Okay.
Mm-hmm.
Okay. So, and there are many like that. Okay.
Mm-hmm.
This is one, the cloud. What was the second step we need to determine? You remember?
You want the distance, the loss function. Yeah, so,
no, that is 3. What is 2?
Sorry?
Agree about.
So yeah, that's the crucial step. For me, it's something which is
I know.
The hardest to understand. How do you choose your functions? You have to have a family of functions that you choose from.
I just added, agree upon a parametric family, right?
Yes.
Let's talk about it. Parametric family of function, right?
Yeah. So it's not going to be polynomial. Not necessarily.
It's not going to be polynomial now. Just a minute. Family of functions. Okay. I will give you an example now of a family which we use, but I want to stress that there is a big space of options
for choice. Okay.
Family. And it's important. And it's all got to do with the Occam razor. You know what Occam razor means?
Yes, I know. I just took a shave this morning with Occam razor.
So please explain what Occam razor means and explain how it's related to what we're doing.
I don't know how to. Occam's razor is be chesroni, how do you say it? Frugal, namely, don't waste. Choose the simplest. So the simplest thing would probably be linear.
The simplest explanation is the best, something like that, right?
Yes. So
okay. Don't overcomplicated thing if you don't need it, something like that, right?
Don't invent the notion of God if you can explain without it. Okay.
I know we will come to that.
Okay.
So let's define the parametric family of function, and I will tell it what we will have. F will be a softmax. Have you ever heard about the softmax?
No. Soft what?
Softmax. Like max, but not a hard max, a softmax. Never heard of it?
Never heard. Not.
Okay.
It sounds like the name of an ice cream. But
a name of a what?
Ice cream. But let's see what it is.
Yeah, should be a good name for naming Ben and Jerry. Yes. Okay, so you don't know what a softmax here is, but you do know what's a multiplication of a matrix with a vector. So I will tell you what's W. W is a matrix of parameters. It will play.
That's the set of unknowns, the thing that you want to look for.
Exactly. That will play the role of the A and B before.
So as I guessed, your functions are going to be linear.
Just this part. I didn't tell you what softmax
is. Okay.
Softmax is not it's not linear. But this part is a linear transformation. So let's you know what X is, right? X is not a secret, right?
Yes. Okay.
Okay, X is just a flattened vector of an image, like with millions coordinations, millions of numbers. W is a matrix. I guess you know the number of rows W must have, right? So here we have n numbers, right? We must, in order to multiply, we need to have this.
The number of columns is n, yes.
Yeah, the number of columns is n also. The number of rows can be 17 if you want. Okay. 17 is the most arbitrary number, right?
Yes, that's the random number is 17. Yes. Okay.
So I will write 17, or sometimes I will write m. I can choose any number I want. It will determine the richness of my family. Let's talk a little bit about the richness of the family and connect it to Occam-Rather. Remember that we were, in our previous discussion, we were talking about a parabola we try to fit on.
Okay, I'm here, yes.
You with me?
Sure, sure.
Suppose we have chosen before a different family of functions. Suppose we wanted to look for a linear function. So it was a different family of function, right? Also determined by two parameters, A and B, the slope and the height, right? In a way, a straight line is simpler than a second order parabola. Why is that? Because it's a subset, right? You can treat a linear function as a special case of a parabola. So this is let's call it a poor family. Abba Ani, Abba Ashir. A poor family and a rich family. What is good about being rich and what good about being poor? Do you have any idea?
Well, I know what Groucho Marx said. I was rich and I was poor, rich is better.
I don't see, no, but in this context, being poor is in a way a good way to generalize. Why? It's like Occam-Rather. You propose a very simple explanation, as a very simple model for what you've seen, and simple is good for general. If you will go to the other extreme and suppose we use not a second order polynomial, but like million order polynomial. We could exactly fit everything, right? Like this, right? Ron, are you with me?
Yes, I'm with you.
And this is called overfitting. What does it mean? I will tell.
There are many possibilities to do that, yes.
Yes, many possibilities, but it is considered a bad way to generalize because the next point probably won't agree with this exact polynomial. So being too rich is problematic. Being too poor might be a simplification. So do you know this phrase that generally refers to Einstein, but he didn't really say it, that everything should be explained in the simplest way you can, but not simpler than that, because it will be a simplification. You know that?
I know this saying, yes.
I don't think Einstein really said that.
No, but Einstein never said all. There is a famous book by Bobby, by the baseball player, Yogi Berra. I didn't say all that I said because he was quoted for, he was overquoted. So
but actually,
same goes for Einstein.
recently I tried to learn special relativity, and I've looked at the Einstein book, and it said something similar there. So it's not completely wrong. Anyway, so this is exactly that. You want to explain this cloud of dot in a simple way, but not too simple. Okay? Okay. So,
but I'm still in the cloud.
you're bothered
about what is softmax. It never told me what softmax.
You're a very curious person. You know, sometimes they say the teachers are the worst students, right?
No, I must know what is softmax. What is softmax?
You must know? Okay. If you must, I will tell you. It's a jump ahead, but I'll tell you because I don't keep any secrets from you, okay?
Okay.
What is the hard max, the regular max that you know of a vector? Like, if it was not soft, like if this is a 8 to 8, this is a vector, just like with 3 numbers. Or what is max? The highest.
Okay.
This is the max. What is soft max? Soft max is like a relaxation of that. I will write it like that. E of I normalized. I will soon explain what it means.
You're now telling me what is softmax?
Exactly, because you wanted to know, even though it's a jump ahead, but I don't keep a secret from you.
Okay, so EI is 0.8 in this example?
Just a minute. This is the softmax in the, okay. Let me explain what I've just written. So if you have a vector x, okay, of any dimension, and you apply a softmax on it, you will get another vector with the same dimension. Okay?
Softmax, the result is a vector as well, not a number, okay?
It's a vector, right? So this is the softmax of x. X is a vector. This is the softmax of this vector. And I wrote here what is the I coordinate of this softmax. Can you read it?
Yes. So you just divide by the sum? Well, this flattens your vector. I know it's okay.
First, I can actually compose it from 2 very simple operations. One is e to the power of x, and the second one is normalizing it. Let me see it this way.
So in this example, it's going to be e to the 0.8 divided by 1 in this case. I know it's over sigma e to the j. Okay. So it's
let us see it in a very, very simple way. You have a vector of point A and point 2, okay? First, I will just make e to the power of 8 and e to the power of 2. But this is not normalized, right?
Yes.
I want it to be a probability, so I will normalize it.
Okay. So softmax, but I don't see the max here. What is max? Where is max?
Think about it a little bit. Why did they call that function a softmax?
I understand. It's
a good name for the function. It's a very good name.
Yes, it punctuates the largest. So the largest gets enlarged. The rich gets richer, and the poor gets poorer.
The largest becomes dominant, right?
Yes. So
do you agree?
The rule is that the rich get richer and the poor get poor. Yes.
Exactly. Like where is that happening? In Israel now.
It's actually from the New Testament, I think.
From the New Testament. Okay, so softmax. Why do we call it softmax, and what's soft about it?
It smoothens things. You don't take only the minimum, the maximal, but you're more lenient, a bit more.
Exactly. Okay. It's something we use a lot in this field of deep learning.
No, this makes sense.
Okay. So now your curiosity is settled?
And I'm wiser now, yes. Okay.
Why did you have to know it in advance?
Well, he threw this fantastic name at me. I was curious. I thought it was an egg ice cream. Now I know it's not. Okay.
Let's get back to W, okay? W is the parameters of the parametric family. It's played the same role as A and B before, right?
Mm-hmm.
Okay, so W here is the matrix. This is W11.
And let me stress again, this is the most important thing to say here. W is our unknown matrix. That's the one we are aiming at, we are looking for.
That's the thing we're looking for, yeah. We're looking for the best value for W to solve our optimization problem. This will be the degrees of freedom we will be playing with in order to find the optimum.
Yes, okay.
So we have many of those. Before we have only two, A and B. Now we have many, many.
We have to wish because you choose your M, right? So you choose.
We have 17 million of those.
Yes. Okay.
So it's we're playing in a really high dimension.
But the 17 you can choose to be 2 if you wish, or 1.
Yeah, right. But the million is given.
Yes.
Like N is given to me. So this is W1 until W1 to N, and here I will have W17.
Now I have the false feeling that I know everything.
What?
Because you've given all the elements of the game to me, or haven't you? My feeling is that you told me everything I need to know. Am I wrong?
Right. So now you can do it yourself. You can program a classifier.
I think so. I mean, the distance. 1 minute.
Distance. We didn't talk about distance yet.
Sorry?
Right? We didn't talk about distance. Yes. The loss function is not.
Yes, the loss function. I don't know what it is precisely.
Yeah. Yes. But here you feel like completely fine with this family of function?
Very much so, yes.
Okay.
But now suppose again. No, I don't. I really retract what I said. I don't know. How do you measure how good your function that you got?
Yeah, right. The loss function, right?
Yes.
Okay. That's our next step. Step 3. Okay. So first, before I defined my loss function, what is the element of the loss function? One of them is the labels, right? You remember how we label dog and cats?
Yes, by 2 vectors, yes, okay.
A dog is this vector, right?
Yes.
And the cat is this vector. So the labels can be only 2 vectors, right?
Mm-hmm.
And what about the value of f? This is a dog and this is the cat. This is the label in my cloud, right? What about the value of
I'm confused. I really am confused. I retract what I said. I don't know where you're heading.
Remember our definition of the parametrics family of function? Softmax of W multiplied by X. W multiplied by X is what size of vector?
M, you said, no? Yes.
M,
17,
yeah,
yes,
we said 17. So it's a 17-dimension vector, right?
Mm-hmm.
Okay. What will be the softmax of it?
Another 17 vector.
Another 17 vector. What will be special about it?
It will be peaked at some point somehow.
And it will be a it will be a probability.
It will be probability, of course.
Yeah, probability. Okay, so the output of F is a probability with 17 numbers, right?
Yes.
Okay. I'm sorry, my mistake. Let's take S instead of 17, let's make it 2, okay? For now. My mistake, sorry. M is, it's 2. It's also an arbitrary number, okay? I want, so now the output of F is a probability with 2 numbers, right? So
you
now
must
I need...
compare it with the learning data, the examples that you're giving. Right?
I'm not following. What are you saying?
So first of all, what is your X? So in each example, you have a different X. So you have your Xi's. This is what you call cloud.
Yeah. Each example is an image of a dog. Let's say my dog, your cat, many of those. That's the X's. And the Y are labels, 0, 1, or 1, 0.
Yes.
Right? That's a cloud. Okay. So we have the cloud. We have F. F gets an image represented as a flattened vector and give us a probability of 2 numbers, right? Like, okay. And what's the label? The label is 0, 1, or 1, 0. So we need a kind of a notion of a distance between what? Between
your outcome and what is in reality.
Exactly. So let's say, for example, my F gives me this distribution, 0, 8, 0, 2. It's an option, right? That might be the output of F. And the label is 1, 0. Because we have only deterministic probability in the labels. So I need to find a distance function between 2 probabilities, right? No?
Yes.
Okay. So do you know a good measure for distance between probabilities?
No. I mean,
Have you ever learned the information theory, Shannon's information theory?
Not really. If you say
It's
Shannon,
a beautiful area. It is a beautiful area. Have you heard about Shannon's entropy?
Yes. So the distance is entropy. So how, in what
Not
sense?
exactly. You don't jump ahead.
Yes. Okay.
So what is an entropy of a P? You
Entropy.
remember
I
the
know.
definition?
Yes. Okay. Perhaps you should tell it because it's the sum of P ln P, right?
It's actually log in the base of 2, not ln,
Okay.
and it's minus. So, and it's actually the expectation of minus log in base of 2 of let's say pi or something like that. Let's write it more exact, like explicit. It's a sum on all. It's a discrete probability, right, with numbers. So I will run to all the, here it's just 2, but if I have n probability value, the entropy will be I to n, a pi multiplied by minus log of base 2 of pi. It's an expectation of minus log.
The minus log, you should stress, is a positive number. Okay, because P is
exactly. This is a positive number because pi is a number between 0 and 1. Log of it will be negative and minus it will be positive. Exactly. And what is the intuition behind this definition? Do you have any intuition?
So let's look at an extreme case when the P is the vector, the PIs are 1, 0, 0, 0, 0. So I don't know what is log of 0, it's a problem, but minus, but 0 log 0 is 0, definitely.
Exactly.
So,
exactly. Right.
so what do you
So
have?
what will be the entropy of a deterministic?
Concentrated on one PI, then the entropy is 0.
Exactly.
Because log
So
2 of 1 is 0.
what you said is for any deterministic probability, the entropy is 0,
Entropy
right?
is 0. Yes, okay.
Okay, that's a good extreme case. What if it's unified probability?
Yeah,
like
uniform. When
yeah,
it's
uniform.
uniform, so it's 1 over n, each of them. So the logarithm of pi is logarithm of n. Yes, a minus, I mean, minus the logarithm. And you multiply it, so it's logarithm of n, and you multiply it by 1 over n. So it is 1 over n log n. So what is so special about it?
Is that correct, what I just written?
Not for me, because suppose it's 1 over n, or you only apply to
Yeah, only
0.
2. You
Only
you
2.
like simplicity.
Okay. No, yeah, but for 2, it's because it's logarithm of 2. It's
You want to 1 over n? Let's do it 1 over n.
so, but the logarithm of no, please bring it down again, because you take the logarithm on the base of 2 of half, it's minus 1. So it's not half times 2, but half times 1.
Oh, I'm sorry. You're right. This is 1, right?
Yes.
My mistake, yeah.
So it's
So
1.
the entropy of this is 1. So let's generalize for n. It will be the same idea. Will be
But then
log,
there will be log of n.
exactly, log of n, right?
Log of
But what? Why do we say Shannon was a smart guy? What's so special about this definition?
So
What's the
if they're
intuition
uniform,
between?
then it's large or maximal, even if they're uniform. If it's uniform, then the entropy is big. If it's deterministic, the entropy is small as possible.
Okay, so
Small
let
entropy means you know things.
exactly.
Large
So
entropy means you don't know.
exactly, entropy is a measure of
Your certainty of how much
uncertainty.
do you know?
Uncertainty. Let me give you a different view, but very similar one. Suppose that I have a probability that you don't know, and I make a, I will choose a random number from the probability you don't know, and you have binary question, and you try to, sorry, you know the probability. You know a probability, and
What
I
are your
choose,
numbers, or what are the possible outcomes?
let me draw it for you.
Either 0 or
Suppose,
1?
no, think of it like that. I have a probability of a quarter, and a half, okay? 3 outcomes.
Yes.
You know this is my probability, and I choose a random number
No,
from
first
this.
of all, there are 3 possibilities, A, B, and C.
Exactly, A, B,
Probability is quarter, quarter, half. Okay.
A, B, and C.
Yes.
Now I choose A, B, and C according to this probability, and you want to ask binary questions, and you want to ask the few questions you can in order to guess my
Your probability distribution, or what?
yeah. So what you will do, the best thing is to ask the first question will be, is it C, right? You understand why is it
I
C
do.
is
I
the best
know your
question?
probability. 1 minute. Do you know? I know your probability distribution.
Yeah. You know my
And
probability.
you had
You
a
don't know
die.
my number.
You had a die. You tossed a die, and you got a result. And I want to know what your result is. So I ask you, is it C? And you say no, because you're cruel. Okay.
You have a decision tree, and now you will ask, is it A, for example?
Yes.
And this is no, so it's B, right? And this is no. This is yes.
Okay.
It's a B. It's a. So you see, this is the best thing you can do. Why is that? It's always best to divide two cases with the same probability. Like, right? It's the same when you play the game of guess my. I will think about a figure, and you want to guess it. You will ask. It's like see a lion in the desert, right? But binary search. You always try to cut things in half, right? So entropy is actually the expectation of the number of questions you will ask if you'll do the best strategy. That's the entropy.
So let's check what you said. If we have a uniform distribution,
No.
In log n.
No, I don't want to think about uniform distribution. Think of
No. I'm just checking what you said.
Okay.
You said it's the expected numbers, and it's
right.
well known. If the distribution is uniform, you need log n, precisely log 2 of n question. And if it's deterministic, then you just, so it's 0, 0, 1. I ask you, did you get C? And you tell me, yes, I got C.
Exactly.
Get C. Okay. And in one question, I knew it. Okay.
Yeah, you don't need question if it's deterministic, right?
So 0 question.
0, yeah. And what about uniform? You understand that in
log n,
you can find it.
Yes.
Okay. But this is a more interesting case. Like sometimes one question will be enough, and sometimes two questions are needed, right?
But 1 minute, suppose it's third. So I ask you what? I ask you, is it C? And in half of the cases, so it's not that you can do it in log, and it's on the average. Right. So I ask you, is it C? And with probability third, you say yes. If not, then I go to the next and so forth. Okay.
Makes sense.
Just please summarize the entropy.
I think we're going to stop here. Is it okay for you to stop here? It's kind of in the middle, but it's long enough.
My old age, yes. Okay.
But let me just emphasize what I've just written here. Entropy is the expected number of questions using the best strategy.
Okay. Okay.
You want to?
No, this is a non-trivial result, what you told.
No, not trivial at all. Shannon was really wise.
That's a theorem of Shannon, probably. Yes.
Actually, I didn't prove anything here, but yeah.
No, you mentioned, you said that the expected number, what's written here, the theorem.
Well, the theorem is, for example, that it's the limit, the lower bound of compressedness of a file, for example, of information. Entropy is the lower bound of compressedness. You understand?
Yes, I think so.
It's also had to do with the notion of Kolmogorov complexity. Have you ever heard of Kolmogorov complexity?
Yes, I heard the name.
Yeah, it's all the same. Or minimum description length. Have you ever heard of that?
This I haven't learned, but okay.
Okay, we'll talk about it. Okay, so Ron, thank you again for helping me.
Yes, thank you for the lesson.
Okay, take care.
Bye.
Bye-bye.